Imagine deploying a massive multi-million-dollar cloud architecture and the entire build just instantly crashes in your automated pipeline.
Oh, man. That is the worst feeling.
Right, and not because of a faulty server or, a network outage, but because no one told the configuration language how to answer a single missing question.
Yeah, it's always the smallest things that take down the biggest builds.
Exactly. So today we are decoding the HashiCorp configuration language, or HCL. We've pulled this deep dive straight from the official Terraform documentation and the Terraform Associate 003 exam objectives.
Which is crucial, by the way.
Yeah, absolutely. Because if
Yeah.
you are aiming to pass that certification, this is the foundational syntax. You have to master it. And we know you already have the basics down, like you know what Terraform is, you understand cloud providers, you get state management, and you know how modules work.
Right. We're assuming you've got that baseline.
Exactly. So today we are zooming in on the guiding metaphor for this entire discussion. And that is, HCL is a blueprint language. Just like an architect uses a blueprint to describe a physical building, you use HCL to describe living, breathing cloud environments.
I really like that analogy. It fits perfectly.
Okay, let's unpack this, because before we can build the skyscraper, we need to know how to read the symbols on the page.
The symbols are honestly the perfect place to start. I mean, you cannot interpret an architect's blueprint without understanding the basic visual language, right?
Right, like what's a door, what's a wall.
Exactly. You need to know which intersecting lines represent a door, how a window is indicated, and which thick lines represent load-bearing walls. In HCL, those core structural components are broken down to three fundamental concepts that you'll absolutely be tested on.
And those are?
Blocks, arguments, and expressions. A block is essentially a container. It defines a specific object you want to create or manage. For instance, a resource block tells Terraform you want to build a piece of infrastructure.
Okay, got it.
That block has a type, like awesome-sense. It has a local name you give it to reference later, and then, a set of curly braces that enclose its specific configuration.
So if HCL is a blueprint, a block is like a specific room in that building. The arguments would be the furniture placed inside that room, and the expressions determine the exact dimensions, color, and style of that furniture.
That structural hierarchy is exactly how HCL is parsed. It's spot on. Inside those curly braces of a block, you define arguments. An argument is just a simple key-value pair that assigns a specific value to a particular name.
Like giving it a label.
Right. You might have an argument called AMI for an Amazon machine image, and you assign it a value. The value itself is determined by an expression. And an expression can be a literal string, a number, or, a complex reference combining data from entirely different parts of your blueprint.
Now, since this is for the Terraform Associate exam, I know they test heavily on data types. And I'm assuming since this is a highly declarative language aimed at infrastructure professionals, the exam isn't just going to ask what a string or a Boolean is.
No, it goes much deeper than that.
Right. It expects you to know how HCL strictly enforces these primitive types. Like if an argument explicitly expects a Boolean, true or false, and I accidentally pass it the string true, wrapped in quotation marks, I would assume the strict declarative nature of HCL causes the build to fail immediately.
Well, actually, it will often succeed,
Yeah.
which is a nuance that surprises a lot of engineers.
Wait, really? It just lets it pass?
Yeah, HCL has this feature called implicit type conversion. If it expects a Boolean but receives the string true or false, Terraform will quietly convert that string into the Boolean equivalent under the hood to keep the build moving.
Oh, wow. I had no idea it did that.
Yeah, and the same happens if it expects a string but you provide a number, it will just convert the number into a string format. However, relying on implicit conversion is a really dangerous habit.
I can imagine it sounds like a recipe for silent bugs.
It is. The exam wants to ensure you understand explicit type constraints, especially when you start building complex modules. Because if you pass a complex object into an argument that expects a simple string, that is when the build throws a hard error.
Okay, so the primitive types like strings, numbers, and Booleans can be somewhat forgiving, but the exam also focuses heavily on complex types, right? Like lists, maps, and objects.
Yes, heavily.
So a list is just an ordered sequence of values that all share the same type. A map is a collection of key value pairs, also sharing the same type. But an object acts like a customized toolkit where every slot holds a completely different tool.
That's a great way to put it.
You could have an object that contains a string for a server name, a number for its CPU count, and a Boolean for whether it needs a public IP.
What's fascinating here is how these incredibly simple structures scale up. I mean, you take these basic data types, insert them into arguments, wrap them in blocks, and suddenly, boom, you are defining massive, intricate cloud architectures.
But if this toolkit is hard-coded into the blueprint, we can only ever build the exact same house on the exact same lot.
Exactly. It's too rigid.
Yeah, like if I want to take this configuration and deploy it to a staging environment instead of production, I can't just rewrite the core files every time. How do we force this static syntax to accept outside instructions?
We make the blueprint dynamic through input variables.
Okay.
If you want to use the same Terraform configuration across different environments, you cannot hard code the dimensions of the house. So you define variable blocks. These act as the external parameters, like the incoming data for your configuration.
So do the inputs.
Right. You define them once, and then you access their values using the var.name syntax throughout your code.
But the exam objectives emphasize that variables are highly customizable. It's not just a matter of naming a variable and leaving the door wide open for any data to flow in, is it?
Far from it.
Yeah.
You have to shave and restrict those inputs. You can define default values, so if a user running the code forgets to provide an input, Terraform has a safe fallback.
That makes sense.
And more importantly, you enforce type constraints. You can demand that an input must be a list of strings, which prevents someone from passing a single string and breaking a loop later in your code. You can also write custom validation blocks.
Okay, so a validation block means I can write a custom rule inside the variable itself. Like, I could say, this variable must start with the prefix prod, or the build will fail immediately, guaranteeing naming conventions are respected before any infrastructure is actually provisioned.
Yes, exactly. And the validation block allows you to provide a custom error message that will print out to the user, telling them exactly why their input was rejected.
That's super helpful for debugging.
It is. Additionally, you can mark a variable with the argument sensitive equals true. This is crucial for exam prep.
Oh, the sensitive flag. I've seen that trip people up.
Yeah, marking a variable as sensitive tells Terraform to redact the value of this variable in the console output. So if you are passing in an API key, Terraform will display it as literally parenthetical sensitive value in the terminal logs. However, and this is a classic exam, trap marking, it's sensitive does not encrypt it in the Terraform state file.
Wait, really? It just hides it in the console?
Exactly. The state file is still plain text, which is why securing your state is an entirely separate exam objective that people need to study.
Okay, wait. If input variables are the key to making things flexible and dynamic, why do we need locals at all? I know the exam tests the difference between a variable block and a locals block. Why not just use variables for every dynamic piece of data?
That's a really common question. The distinction comes down to who is controlling the value.
Who is controlling it? Okay.
Yeah. Input variables are set by the user running Terraform. They are the external levers. Local values, defined in the locals block, are internal expressions used strictly within the module itself.
Oh, I see.
They are not exposed to the user at all. It comes down to the DRY principle. Don't repeat yourself.
So if I have like a complex tagging structure that combines a project name, an environment variable, a billing code, and a timestamp, I don't want to calculate that massive string 50 different times across my resource block.
Exactly. You calculate it exactly once inside a locals block, perhaps calling it local.common tags. Then you just reference local.common tags on every single resource.
And if it changes?
If the company changes its tagging policy tomorrow, you only update it in that one single place. So variables are for external flexibility, locals are for internal cleanliness and logic.
Got it. Okay, but once you allow all these external inputs to start changing the blueprint, you inevitably get conflicting instructions. It's like a construction site where the project manager, the client, and the local zoning laws are all handing the form in different sets of plans. Who wins?
That conflict introduces the concept of variable precedence, which is heavily tested. Terraform has an uncompromising order of operations for resolving conflicts when a variable is defined in multiple places simultaneously.
So if I have an environment variable telling Terraform to build a small server, but I accidentally type a command line flag asking for a massive server, the system has conflicting orders. I would assume the environment variable acts as the foundational rule and blocks my typo.
It is the exact opposite, actually.
Oh, really?
Yeah. Terraform prioritizes the most immediate, deliberate human action. The hierarchy starts at the very bottom with default values in the variable block itself. Those have the lowest priority.
Makes sense. They're just fallbacks.
Right. Above defaults are .tfvars files, which engineers use to define standard environments like staging or production. Above those files are environment variables on your machine, specifically ones prefixed with tfvar.
Okay.
And sitting at the absolute top, with the highest authority, are CLI flags using the -var option directly in your terminal command.
So the command line interface overrides everything beneath it because typing the flag is the most immediate intent at the exact second of execution.
The CLI always wins. CLI flags beat environment variables, which beat .tfvars files, which beat default values.
Which brings up the trap. What happens if the foreman is waiting for an instruction, but no one says anything? Like if a variable has no default value defined and absolutely no value is passed via a CLI flag, a .tfvars file, or an environment variable.
That behavior changes entirely based on the context of where the code is running.
How so?
Well, if you are sitting at your laptop running Terraform interactively in your local terminal, the system simply pauses. It prints the name of the missing variable and prompts you to type in a value right there on the screen.
It literally asks you to fill in the blank on the blueprint.
It does. But if you are running this exact same configuration in an automated CI/CD pipeline like GitHub Actions or Jenkins, there is no interactive terminal. There is no human sitting there to see the prompt or type the answer.
Uh-oh.
Right? In that context, Terraform cannot prompt for input, so it instantly fails and the pipeline errors out.
Here's where it gets really interesting. Because the exam isn't just testing if you know the definition of a variable. It's testing if you understand the context of the execution. Knowing whether you are running locally versus running in an automated pipeline changes the fundamental behavior of the tool.
Exactly. You have to read the scenario questions carefully. Look for clues about the environment. Words like automated pipeline or non-interactive completely change the answer to the question.
Okay, let's shift gears a bit. The virtual walls are up, the resources are provisioned, and the build is complete. But the house isn't connected to the grid yet. In our HCL metaphor, outputs are the exposed plumbing pipes and electrical wires sticking out of the walls, allowing completely separate systems to hook in and share resources.
I love that. Outputs are the data bridges of Terraform. You define them in an output block, and their primary job is to extract specific pieces of data from your newly created infrastructure.
So data can leave the module?
Exactly. If Terraform builds a database, your application servers in a completely different module need to know the IP address of that database to connect to it. Output values expose that specific IP address so other modules or the end user can consume it.
And just like input variables, I assume outputs can also utilize the sensitive equals true argument. Like if my module generates an administrative password for that database, I need to pass it to the application module, but I definitely don't want it printed in plain text on the screens of everyone watching the CI/CD deployment logs.
Spot on. You add sensitive equals true to the output block, and Terraform will securely pass the data internally between modules, but redact it as a sensitive value whenever it prints to the console.
That's a lifesaver.
It really is. However, raw data pulled from an output isn't always in the exact format the next system requires. Sometimes the data needs to be manipulated, counted, or formatted before it is handed off. And that is the domain of HCL's built-in functions.
And the documentation is very clear here. You cannot write your own custom functions in HCL. You have to master the extensive library of built-in functions they provide. So rather than just reading a list of definitions, let's look at how these functions actually solve mechanical problems during a cloud build.
A great example is the merge function. Imagine you have a map of mandatory corporate security tags that must go on every server, like the billing department and compliance level.
Standard enterprise stuff.
Exactly. But you also have a separate map of tags specific to a single developer's temporary project. You cannot apply two separate tag arguments to the same server.
So what to do?
You use the merge function to automatically combine those two maps into a single unified map before Terraform applies it to the AWS instance. That ensures total compliance without forcing the developer to manually type out all the corporate tags every single time.
Another powerful one the exam loves is the template file function. Like, if I am spinning up a new virtual machine and I need to pass it a startup script, say an AWS user data script, to install a web server, I don't want to hard code the entire bash script inside my Terraform configuration file. It gets too messy.
Right. You use template file. It reads an external file from your disk. But unlike the basic file function, which just reads static text, template file allows you to pass Terraform variables directly into that external file.
Oh, that's incredibly useful.
Yeah, you can have a generic bash script, and Terraform will dynamically inject the specific database, IP address, or environment name into the script right before the server boots up.
And what about handling missing data? Because things change. If I am looking up an Amazon machine image ID based on the region I'm deploying to, what happens if I deploy to a new region that isn't in my map? Doesn't it crash?
That is where the lookup function is critical. It retrieves the value of a single element from a map based on a given key. But its superpower is the fallback argument.
A fallback.
Yes. You can say, look up the AMI for the US-West region in this map, but if that key does not exist, use this default AMI instead. It prevents your entire deployment from crashing just because a single key was missing from a complex data structure.
So functions are basically the power tools of the blueprint language. Instead of manually counting items in a list, formatting strings, or writing complex conditional logic to avoid missing data, you just use length, toString, or lookup to automatically shape the data on the fly. You aren't doing the manual labor, you're letting HCL do the heavy lifting.
If we connect this to the bigger picture, mastering these functions is what separates a novice who hard-codes everything from an expert who writes elegant, dynamic module architectures. A novice writes 10 different static configurations for 10 different environments. An expert writes one dynamic configuration that uses variables, locals, and functions to adapt itself automatically.
I think we've got a solid grasp on the mechanics here. We understand the syntax blocks, the type constraints, the strict rules of precedence, the internal logic of locals, and the data bridging power of outputs and functions. But theory is one thing. Sitting down and passing the Terraform Associate 003 exam is another.
Very true.
Let's put this to the test with 3 rapid-fire exam-style scenarios based directly on the mechanics we've just covered.
Oh, I like this. Let's run through them.
Scenario 1. This tests variable precedence. You are an engineer who has defined a variable block for instance type with a default value of t2.micro. However, you also have a terraform.tfvars file in the same directory that sets instance type to t3.large. Finally, a colleague triggers a pipeline run, and the script executes the command, terraform apply -var instance type m5.xlarge. What size instance is actually built and why?
Okay, the instance provision will be an m5.xlarge.
Yeah.
On the exam, you have to mentally walk up the hierarchy of authority.
Let's trace it.
The default value of t2.micro inside the block has the lowest priority, so it is immediately overwritten. The .tfvars file pushes the value up to t3.large. But because the command was executed with a -var CLI flag, that flag claims the absolute highest precedence.
Yeah.
The command line interface always wins, so m5.xlarge is the final answer.
Perfect. Scenario 2. This is all about the context trap we talked about. You have a Terraform configuration with a required variable called db_password. There is no default value defined in the block, and you did not commit a .tfvars file to your repository. You push this code to your automated CI/CD pipeline, which simply runs the command terraform apply -auto-approve. What happens next?
The pipeline fails immediately.
Instantly.
Because db_password has no default and no value was provided via a file or flag, Terraform absolutely needs that data to proceed. If this were a local interactive terminal, it would pause and prompt the engineer to type the password. But because it is running in a non-interactive CI/CD pipeline, Terraform recognizes it cannot prompt for user input. It gets a dead end and throws an error.
Excellent. Scenario 3, the final inspection. You have written a module that provisions a highly secure database. Terraform uses the random provider to dynamically generate a complex password for this database during the build. You need to pass this generated password to a completely separate web server module so it can connect, but you absolutely cannot have this password showing up in the terminal logs when the pipeline runs. How do you achieve both goals?
You handle this entirely in the output block of the database module. You declare an output to export the generated password, which creates a data bridge for the web server module to read it.
But what about the logs?
Inside that output block, you must set the argument sensitive equals true. This ensures Terraform passes the data internally between the modules, but aggressively redacts it as a sensitive value whenever it prints the execution plan or apply logs to the console.
So, what does this all mean? It means the exam isn't just checking if you've memorized a dictionary of HashiCorp terms. It's testing if you can blend them together mechanically. Can you take syntax rules, inject dynamic variables, resolve their conflicts objectively, and safely output the results without breaking the automation? That's the real test.
To synthesize our entire dive today, HCL is not just arbitrary syntax you have to memorize. It is a highly logical, rule-based blueprint language. Input variables customize the external dimensions of the build. Strict precedence rules resolve arguments when multiple blueprints clash. Locals keep your internal logic mathematically tidy, and outputs serve as the exposed wiring connecting your build to the rest of the world.
Everything has its place.
Exactly. If you understand the flow of data from the input variable all the way through the functions to the output block, you are going to excel on this section of the exam.
And beyond the exam, mastering these concepts isn't just about getting a certification badge to put on your resume. It's about writing clean, bulletproof infrastructure code. Code that your entire engineering team can rely on, read easily, and deploy without fear of catastrophic overwrites.
This raises an important question about the ultimate scale of this logic.
Yeah, I want to leave you with one final thought to mull over. If variables act as the inputs to a single module and outputs pass that data out, imagine how complex and powerful infrastructure could become when the measurements, the outputs of one massive cloud architecture dynamically become the parameters, the inputs of entirely separate architectures across the globe. You're no longer just drawing a single blueprint for a single house. You're writing code that creates an interconnected, self-sustaining city of infrastructure where every building talks to the next. Good luck on the exam and happy building.